This is Lab 5, Faraday's Law. So the problem in this lab is that we need to visualize the magnetic field, force, and induced current of a strong bar magnet falling through a conductive tube. The results overall show that dB over dt and velocity decreased over time, and the sections that we'll go through include the model, physics principles related to the lab, experimental setup and coding, and final questions and conclusion. So the model in this lab, a bar magnet was dropped through a tube of aluminum and the time in the tube was recorded. And we had to use an aluminum tube because you cannot use a ferrous one, which is usually magnetic. The computational model was a magnet modeled as a dipole and a tube modeled as a stack of non-interacting conductive rings. So the principles used in this lab, there's 4 principles. The first one is Faraday's law, which says that the change in the magnetic environment of a coil of wire causes a voltage to be induced, which then causes a magnetic field and exerts a force. We use this to calculate the induced current in each ring by the magnet. The Biot-Savart law says that magnetic field is related to source current, and we use this to calculate the force on each ring by the magnet. And Newton's third law says that every action has an equal and opposite reaction, and this was used to calculate force on the magnet by the tube of rings. And Newton's second law says that acceleration is directly proportional to magnitude of net force in the same direction of net force and inversely proportional to the mass of object, and we use this to model the motion of the magnet. So the experiment data, the average time that the magnet spent in the tube was 1.28 seconds, and here is the geometry of the tube. And the geometry was plugged into the coding for the lab, as you can see on the left, and then on the right the bar magnet was created. And then after this, several functions were created for calculating things such as the magnetic field of the bar magnet and the magnetic flux, the current in the rings, as well as the net force on the magnet. And here's a visual output of the coding, and as you can see, there was a sharp decrease in velocity that eventually evened out. So interpreting the simulation, which color corresponds to clockwise and counterclockwise, and how can you know? So the simulation displayed blue rings, and we know that the change of flux is down. So the current here would be counterclockwise, which means that red would be clockwise. And what happens to the dynamics when you flip the magnet around? The dynamics would not change because flux is still going down, and therefore current would still be counterclockwise, and the force would be the same cross product. How does the total time in tube of the computational model compare to the real time measured? How can the simulation be made more accurate? So the simulation showed a much shorter time than the actual experiment, and it could be made more accurate with different values of mu, or by adding more rings in the simulation tube. And what does the shape of the graph say about the forces acting on the magnet? So the shape of the graph shows that the forces are consistent throughout the length of the tube because the only variation seen in the graph was at the very start when the magnet was still outside of the tube. And final questions, what if the resistivity of the conductor was reduced as close as possible to 0? How would the dynamics of the falling magnet change? So the induced currents would be bigger and therefore the magnet would fall more slowly. And then what if holes or slots were cut into the tube? How would this affect the ring currents in your model? The magnet would fall faster because there would be less force from the rings on the magnet.